Hi, so today I am teaching 5.4 belts and bearings, which I think is a really cool topic. There's one equation that you need to know, T2 equals T1 times e to the mu times beta. Okay, I'm going to explain every single term in that equation here. T2, right? I guess here I should explain belts and bearings first. So in our example up here, we have B. It's some sort of cylinder, right? And we have A, which is some sort of rope wrapped around B. Okay, and there's friction, right, with that, and the friction between A and B is going to affect how much force we have to exert over here to stop the force on the other side, right? You can also calculate how much it takes to move the force on the other side. Okay, those are two different numbers, right? We can exert, this is a 5-pound force. I'm just throwing out numbers, but we could exert 3 pounds, right? And the friction is going to help us, right? It's going to stop that. Everything's going to be at equilibrium, so everything's going to stop, even though there's 5 pounds over here and 3 pounds over here, because there's friction involved, right? If they were equal, right, it would also be stationary, but it's also going to take more than 5 pounds for you to move this force over here, right? Because of the friction involved. And so what these two T's are, they're the forces on either side of this belt or bearing. And so the 5 pound and the question mark would go in for the TE or the T1, the T2 or the T1. And so the difference between T2 and T1, right, is that the T2 is parallel with the impending motion. That's how I like to think about it. So if you wanted to stop this 5-pound force, right? You wanted to exert enough force to stop this 5-pound force. You would the impending motion would be this way, towards the 5 pounds, right? So the 5 pounds would be right here, because the force is parallel with the impending motion. Okay? If you were trying to pull the 5 pounds, not just stop, pull, right? The impending motion, instead of this way, is this way. Okay? It's towards our question mark. And so the question mark would be right here, it'd be T2, because that's the force that's parallel with the impending motion. Okay, so the impending motion depends on the context of the problem. Okay, well, we're gonna do it both ways. This problem, we're gonna stop that 5-pound force. In this problem, we're gonna move this 100-pound force. And so we can get right into it. Or I guess I'm sorry. I should keep explaining. This force right here is parallel with the friction. It's in the opposite direction of the T2. Okay, so if 5 pounds goes here, the question mark goes here. If the question mark goes here, the 5 pounds goes there. E, right? We all know what E is. Mu is the friction constant. Okay, that's something that you're going to be given. That's something that you're not going to have to calculate. It's the static friction between two objects. That's a known number. You can find that on a chart or wherever. In this case, we don't have specific materials. This is a made-up problem. So we're going to say that mu is 0.3, and it's 0.2 over here. Beta, okay, that's might be a little tricky. Beta is the distance the objects are in contact in radians. Okay, so the circumference of this circle happens to be the distance, right, that the rope and the cylinder are in contact with each other, okay, because it's wrapped around only once. And so in this case, beta would be 2 pi, okay, which is in radians, that's 360 degrees, that's an entire circle. And so we'll get right into it. In this case, we're trying to stop the motion, okay? There's a big difference. If we're trying to move it, it's different, okay? We're trying to stop this force from being pulled. And so our impending motion is this way, okay? T2 is parallel with the impending motion. So I'm going to copy down this equation, e to the mu beta. Okay, so our T2 is 5, our T1 is unknown. Okay, we're calculating how much force it's going to take to stop this with the friction on our side. We're going to multiply that by E times 0.3 times 2 pi. Right, I went over why that's 2 pi. It's just the circumference in radians. It's 360 degrees because it's only wrapped around once. So when you do that math, T1 is going to equal out okay, so after you do that math, this is what you're going to get for T1, 0.759 pounds. I mean, you barely need to pull on that rope for it to stop, you know. Really what's happening, this rope is barely moving because there's so much friction. 5 pounds isn't really a big enough force to move the rope. It is moving. If you don't have any force over here, it's moving. But in order to make it stop, all you have to apply is 0.7 pounds because the friction's on your side. Right? And this is to make it stop, okay? Emphasis on that. This right here, okay, this is a person holding onto a rope, they're pulling it, okay, this is a rock, and the rope is on the rock, connected to a big pot of gold, okay, it's 100 pounds of gold, right, there's a lot of money on the end of the rope, so this person wants to pull it up, they want to move it, okay, they don't just want to stop it from falling, they want to pull it, they want to move it up. And so the impending motion is this way. Okay? They want to pull it up. Right? They want to go. Okay? The equation here is T2 equals T1 E mu beta. So the force that's parallel with the impending motion is our unknown, okay? The force that's parallel with the friction, right? If the impending motion is this way, then the friction wants to go this way, okay? And so that force that's parallel with the friction is 100 pounds, okay? Mu is 0.2. Mu is the constant, the friction constant between the rock and the rope. And beta is the distance, right, in radians that the two things are in contact with each other. So I wrote here, it's a quarter circle, okay? And so a quarter circle with 90 degrees in radians, right, is pi over 2. So when you calculate that, okay, so when you calculate that, you get T2 equal to 136.9 pounds. And so what this person has to do, which makes sense, because what this person has to do is move this bucket of gold, right, this 100 pounds up. Okay, they're trying to move it. The impending motion is towards them. Right? If they were trying to stop it, it should be less than 100 pounds, but since they're trying to move it, the friction is not on their side, and they have to apply more force than what is on the other end of the rope. And so yeah, essentially, there's really two ways you can solve for this problem. The first way is to stop. Right, the impending motion is towards the object you're trying to stop, and you can apply this equation to it to get the amount of force needed to stop. You can also apply this equation to find the amount of force needed to go. The amount of force needed for you to pull up, a bucket of gold off a cliff. If you ever need to calculate that. But there's two ways. And I want to put emphasis on that: go and stop. So yeah, that is belts and bearings.